It's super valuable in biological systems to be able to take a glucose molecule and to phosphorylate it. So start with a glucose molecule and phosphorylate it. And the reason why is once you have this phosphate group, let me make sure I put that charge right over there. Once you have this phosphate group, or once you have this negative charge on this glucose 6-phosphate, it becomes much harder for it to leave the cell. The cell wants to hog as many glucose molecules as it can. When the glucose isn't charged, it's able to pass through the cellular membrane, but then once it becomes phosphorylated, it's going to stay in the cell. And glucose 6-phosphate right over here, this is a very important input to a whole series of processes inside of cells. Now, unfortunately, this reaction of taking glucose and phosphorylating it requires energy. It's endergonic. It's not going to happen spontaneously. It has a positive delta G. It is endergonic. And so you can imagine what we're going to need to make it happen. We're going to have to use the energy currency of the cell, our good friend ATP. And the way that we're going to make this reaction happen is we're going to couple what's essentially, you could view it as a hydrolysis of ATP, although we won't have exactly a water molecule in the mechanism, but what's functionally the hydrolysis of ATP into ADP in a phosphate group, which is very energetically favorable. It is exergonic. It would happen spontaneously under the right conditions. It won't just always happen inside of an aqueous solution. It needs a little bit of activation energy or an enzyme to lower the activation energy, but the net reaction, it is exergonic. So what we can do is we can couple these two reactions. And so when we couple the two reactions, we have ATP plus glucose reacting, and there we use an enzyme, the general term for it is hexokinase, to facilitate this reaction, to lower the activation energy. It's going to yield glucose 6-phosphate, glucose 6-phosphate, and ADP, and ADP. Now, what's the delta G for this reaction going to be? Well, it's a coupled reaction. You can view it as a combination of these two reactions. And so, roughly speaking, you can say, well, let's just add the delta G's. So if you add the delta G's here, you're going to get, if you add this negative delta G, this exergonic and this positive delta G, you're going to get negative 30.5 plus 13.8. That's going to be negative 16.7 kilojoules per mole. And so this coupled reaction is going to be exergonic. Not quite as exergonic as a hydrolysis, because now you're going to be using some of that energy, but this can happen spontaneously, especially if you can lower the activation energy enough for it to happen. And so let's now look at the mechanism of how it happens. Now, without an enzyme, the way that this reaction needs to occur is that you have an electron pair right over here on this hydroxyl group, that it needs to do what's called a nucleophilic attack on this phosphorus right over here. But without an enzyme, it's going to be very hard for it to do it. It's going to have a high activation energy because it's going to be impaired by all of this negative charge from these oxygens right over here. You can imagine electrons don't like going through a lot of negative charge. They're repulsed by negative charge. So we're going to need an enzyme to help facilitate this reaction, to help lower the energy to actually start, and essentially get these electrons out of the way. And the enzyme, or the general term for the enzymes that do this, is called hexokinase. And hexokinase, let me write this down. Hexokinase. And the way it does is it provides ions to, one way to think about it is to keep these electrons over here busy. And in particular, it has a magnesium ion right over here. And this is bound to the rest of the hexokinase. Remember, this is all happening in 3 dimensions, so the hexokinase is kind of wrapping around it. So these can keep these electrons busy. There's other ions on the hexokinase that can keep these electrons busy. Other positive ions keep these electrons busy. And so these electrons can sneak in and do the nucleophilic attack. And remember, when we talk about enzymes, these are these protein, let me do the same color that I wrote the hexokinase in. These are these complex protein structures right over here, just like this. And so you might have the magnesium ion. Let me do that in that purple color. just right over there, and then maybe the glucose molecule gets bound right over here, and then maybe you have your ATP gets bound right over here. And I'm just kind of giving you an example. This isn't exactly what's happening, but by essentially wrapping it with this positive charge, it's able to pull the electrons away to help facilitate this nucleophilic attack that needs to happen for the reaction to proceed. And so this bond right over here between this oxygen and this phosphorus, that is going to be this bond right over here. And as this happens, then this character, then these two electrons can be taken by this character, and so that this oxygen is this oxygen right over here, and now has a negative charge. And so what we've just resulted with is glucose 6-phosphate and ADP. And it's energetically favorable. It's exergonic. It's going to happen, assuming that you have the enzyme there to help distract these electrons, lowering the activation energy. And I know what you're thinking. We had this hydrogen right over here, so this hydrogen should be right over here still. And then another water molecule could come and nab the proton, the hydrogen proton, and so you're left once again with just the glucose 6-phosphate. So this hopefully gives you a sense of how reaction coupling occurs, and also a sense of how ATP is actually useful. When I first learned about ATP, I'm like, okay, fine. It's, it really wants to let go of this phosphate group. It's energetically favorable. But how is that actually used to drive things, to actually do to do things in the system that might not be energetically favorable? And hopefully this gives you a sense of how it's done, and also the importance of an enzyme in facilitating it.